what is your favourite number over 1,000,000? Hashtag MegaFavNumbers. Mine is this lovely number up here, or roughly 4.97 times 10 to the 57. But why? Glad you asked. That's how many ways you could build a maze like this and have different orientations and setups. So, how do I get that number? Using this. But let's back up a little bit. So, I love mazes, and in high school I discovered this shape right here in a book called Mathematical Origami by David Mitchell. It's called the skeletal octahedron, and you can see it would have 8 sides like an octahedron, but the sides sunk in. And I just thought it screamed maze. So, just like an M.C.Escher picture, you could walk up the walls or go through to other sides, and you can see I've done like a little example here. Now, before we delve into the 3 dimensions of this weird branch of mathematics, or twig of math, which I don't even know exists or not, I nickname it Maze XYZ, but let's start on 2 dimensions first. So, a maze is, to me, is just a bunch of cells, and you can walk from to any adjacent cell, and a good maze has walls dividing some. So we throw some walls in, great, now you can't get through everywhere. This maze you've got some dead ends, that's okay. Some good mazes would maybe even have a couple ways to get there, to confuse people. Say now we make it so the start and finish are inside the maze, a little part of it. Now imagine you could randomly move start and finish around. So this would be a bad example. What if you started in here, or had to finish there? You're trapped. You can't go anywhere. This is a double dead end. And we don't want those. We also don't want loops. So examples of those, here's a double dead end, here's a loop, and a loop to a dead end. You can imagine those in a maze would be kind of rubbish if you're starting and ending at random spots. So if you had a loop here, this is a non-starter. So a maze can't have that. Also, I'm allowing like branches over because we're in 3 dimensions, so that's fair game. It doesn't matter how many times it twizzles around. This is still an odd number of crossings, so in my mind, topologically, this is the same as the top one. With me so far? Great, you've got no choice, I'm carrying on. So, I also want this to be interchangeable. You could grab any 2 cells and swap them, or as close to as possible. So, you can see here we've got like a little example of 9. You could imagine swapping those around and trying to build a maze. This guy doesn't belong. They've all got 4 exits. This one's got 5. He doesn't belong. Okay, so keep that in mind. Now let's take it up to 3 dimensions. So, little drawing of what we got here. Our cells are going to be these individual triangles. Or if you can imagine one I've already made earlier. You've got all these different pathways walking between them, and each of them are individual cells. And you could decide to swap some of the cells around. So take this one off, put it there, put this one there. You're still good. All the doorways all line up, and you're still good to go. Still a valid maze. Great. But we need to determine how big it's going to be. Now, let's back up first. Imagine your little character here. He's got a couple of different things he could do in the maze. He could step up onto the wall. Lovely. If all he could do was that, he'd be stuck in this room of 3 cells. He's not going anywhere. That's boring. And wouldn't work. Then, only things he could do is go through a door. So we've got a little door drawn here. He walks through to the other side. Piece of cake. Again, if we only had doors, he'd only be able to walk on one plane. And on one side of one plane. That's not going to work. We need a mixture of both. But hang on. Notice we walk on this triangular cell. We went to the left to go through that door. When we came out, we were on the right. So this has to be a fixed distance away. If everything was the exact same, we'd end up in a weird situation where you'd come out of one door straight into another. So half the pieces have to be a mirror image of the other ones, or a red room, blue room, red room, blue room, alternating, and red and blues of slightly different dimensions, a mirror image down the centre, if you will. And similarly with those paths, I'm walking up the left here, but on this tile, I'm arriving on the right. So the paths come in pairs, doors come in pairs across. So we've got some limitations here, but we can make it work. And you can see that red-blue design already on this one I've made, so you can see how they alternate, and it resolves that whole issue. No problem, we can work with that. But the size. So now we know we've got to have pairs of paths, and you've got to pick how many doors. If it's just one door on each cell and one pair of paths, that's boring. It's pretty much just a path around the whole maze. You can't really put in too many walls in our previous flat example, and already it's totally locked off. Other end of the spectrum, if you have, you can go as big as you want, but 4 doors and 4 pairs of paths, each cell has 12 options going at, this is getting insane. So to find some balance here, I found for this one the best was 2 doors, 2 pairs of paths, and all my numbers were done on this. But you could do all the calculations I've done for every size and other shapes. Skeletal cube doesn't work as well, but that's the next best candidate. Let's stick with this and that size for now. Alright, so imagine drawing a network to understand how well connected everything is. Each triangle cell will be represented with a black dot, and paths going in between neighbouring cells in that same room, they'll be orange. Paths going through doors, they'll be green. We'll just pull everything out and make it all see-through and draw a network. We get this. Oh, kind of reminds me of the cube octahedron. It's like halfway between a cube and an octahedron. So, I don't know if you can quite see it, but there's double lines, that are double orange lines between each of the nearby black points. So that's what we've got there. And our job is to go through and figure which lines we can erase. Because at the moment, that's as though every single cell can walk to each of its neighbouring cells any way it wants. Like a giant British roundabout of 6 exits. Every tile looks just like this. Again, that's no maze. That's full connectivity. That's an empty grid in that previous example. So, we're going to come through and erase a bunch of paths and see what we get. So, first up, we need to deal with some troublemakers. Actually, let's deal with them last. First up, we look at how many ways we could organise the finished ones. That one we can do nice and easy at the start. There's 3 cells in each room, there's 8 rooms, so 24, or 12 of each, 12 red, 12 of the blue. So, but this isn't the, we can have it oriented a bunch of different ways as well. 12 different ways, in fact. So, so not 12, 24. So we need to have 11 factorial times 12 factorial, and that's how many ways we could get the finished set of 12 red tiles, 12 blue tiles put on here. Easy. Piece of cake. Next up though, we've got to pick that set of 12 and 12. Now, how I got to this smaller subset, that's tough. We'll do that last. Our set of candidates whittled down from 207 on each side. We've got 29 on the left and 34 on the right. We need to pick 12 from each. So, let's try picking, this guy. That was a 1 in 29 choice, and a 1 in 28. Keep going until you've got 12. How many ways to do that? So, we can multiply all those together. We're just looking at the denominator. So, 29 factorial gets us pretty close to figuring that quickly, but we only want the first 12 in that series. So we can divide it by 17 factorial. That chops it off here and just gives us the part of the series we want. Excellent. Then we can do that on the other side, the mirror image. We've got 1 over 34. We want only down to the first 12, down to 23. So again, 34 factorial over 22 factorial gets us that portion.
Multiply that all together and we get 6.53 times 10 to the 33. Different ways of picking our 12 and 12 from the final candidates. Cheeky bit of brown paper for you number file fans out there.
Now eliminating the troublemakers. There's loads of ways to make all sorts of trouble. Double dead ends. Easy, we can just knock out all the tiles that have more than one dead end. That's over 100. Gone. Next up, we have dead ends that come from one tile to another, but still a dead end. So we can eliminate 120. Now those, we can still allow one. So we've got a choice of 1 and 120, which one we're going to pick and keep in the set of candidates. But there's more than just dead ends. There's loops, and there's loops to dead ends. Oh, I'll just do one example so you get a taste for how it goes. Say we've got a loop just on the very top there. That would be like having a loop and just one room here between two tiles. There's loads of others. So that would be made with these two tiles. It's the same way. There's 4 ways of making each of them from the tiles we've got left. These 4 or those. We've got to eliminate one set. If we get rid of all of these, we're good. If we get rid of all of those, we're good. So a choice of 2 for the red and a choice of 2 for the blue. Mutually exclusive. So there's 4 ways we could pick to eliminate those troublemakers. Great. So there was a choice of 120, then a choice of 4 for this rule, and so on and so forth. All of those multiplied together, you get 39,813,120. And that's just the taser. There's so many other different ways we could break the maze and make it disconnected in different parts that we need to deal with. So that's what all those rules are for, and it would take hours for me to explain everything. And it's probably wrong anyway, because I'm doing this for the first time. I don't think this is very conclusive. But that's how we get our 3 parts. The number of ways we can eliminate the troublemakers, the number of ways we could get those safe candidates down to our final 12 and 12, and the number of ways we could organise them on that shape. And that is how we get the different number of ways to make this maze. My favourite number over 1 million, 4.97 times 10 to the 57. What's your favourite number over 1 million?